All right, we're back to talk about some of the impacts to whether energy that arrives in the Earth system is trapped or stays here for a long period of time, or whether it's bounced back. So this is kind of part of our outgoing energy budget component. So let's share our screen. Okay, so albedo is another word for reflectivity. And the reflectivity of the Earth is not something that is actually consistent over time. Both the surface of the Earth and the atmosphere of the Earth can change in terms of how much energy, both light and heat energy that arrives, is bounced back to space or is absorbed and held for a period of time. So currently, about 70% of the SR or solar radiation or insolation is absorbed by the Earth's surface, which means that the other portion, 30%, is really readily just bounced right back to space and never really has an impact on warming the climate. And again, that's something that is true today on average across the Earth, but it's not a measurement that has been consistent over time. We've had periods during ice ages or during warm periods where that number was considerably different. So the reflection is changing over time, or the albedo is changing over time. Something that has a high albedo is very reflective. Something that has a low albedo is not very reflective. So you might just be able to think yourself of some things that are reflective that you've interacted with over time, or things that are very absorbent. So things that are reflective are going to be very bright. They're going to be hard to look at, and they might also be cold because they're not holding energy. Whereas things that absorb radiation are not going to be bright. And on the other hand, they're going to absorb energy and they're probably going to heat up quickly. So some things that reflect radiation are generally lighter in color. So that might be like clouds up in the atmosphere, ice and snow, particles from volcanoes or from fires. When those things are in the atmosphere, energy from the sun can bounce off them in the atmosphere before the energy ever makes it down to the ground where we are. So it's darker on the ground below the clouds or below the ash than it is above as a result of the albedo, high albedo, or reflectivity of that material in the atmosphere. So I have a picture here of the Care Bears. They should all be wearing sunglasses. They wouldn't be so cheerful up there in the clouds without any eye protection on. Cloud cover is one of the brightest things in the sky. And when there's cloud cover, it reflects lots and lots of energy back out to space. And therefore, it's darker for us down on the Earth's surface on days where there's lots of cloud cover. Snow is another thing. It's very bright. It's very cold. You wear like goggles or glasses when you're in the snow because it's so bright, and it's also cold because it's not absorbing energy. On the other hand, darker surfaces tend to be better at absorbing energy. So this could be man-made things like roofing material or asphalt. And so areas that have a lot of asphalt and tar and things like that tend to be warmer than naturalized areas around them. Sometimes this is referred to as the urban heat island effect, where urban areas are a little bit hotter than the countryside and similar latitudes and similar conditions because of the low albedo of the surfaces, the low reflectivity or high absorbance of those surfaces. And then both vegetation and soils are much better at absorbing energy compared to really light colored surfaces like ice, like snow, like clouds. So here's a image or a map of the Earth. And in this case, we are looking at different colors representing different albedo percentages. So 100% albedo would mean that you're reflecting every single amount of energy that ever comes down or ever arrives at the Earth system. So 50% is you're reflecting 50%. Remember, today on average, we are reflecting 30% and absorbing 70%. So these different areas of the Earth have somewhere on the range of like 10 or 20% albedo up to like 50% albedo. So you can look around and imagine for yourself some of the areas that are high and some of the areas that are low, and then imagine why that might be. And so I'll give you some hints. First of all, up here where it's generally far from the equator, it's going to be covered with lots of ice and snow. These areas like Siberia, Scandinavia, Greenland, Iceland, Canada, Alaska are going to have lots of snow. That's very reflective. But also we have high albedos in places like Africa and the Arabian Peninsula. And these areas are not cold, they're not covered in snow, but instead they're covered in light colored sand, which is also very reflective. And then on the other hand, places that are covered with lots of vegetation, like the Amazon basin, like the Congo basin, like some of the other forested areas around our country on the East Coast and Central Asia and China, etc. These areas are going to be more absorbent, so their albedo is going to be lower. So high absorbance, low albedo, high albedo, low absorbance. Those things are always opposite from one another. Okay, so the albedo of the landscape is something that's not consistent over time, as we've already said. And what can start to happen is that once a landscape's albedo starts to change, it can get caught in what's called a positive feedback cycle. So a lot of time students hear that term positive feedback cycle and imagine that's something that's positive, like thumbs up, a good thing that they would want to see going on in the environment. And in fact, positive feedback cycles are usually not positive. They usually are cycles that lead to rapid changes in ecosystems, which are very difficult for organisms to be able to be accustomed to or adapt to. So what positive means in this sense is more of like a mathematical positive, where a change in one thing is gonna elicit the same kind of change in another thing. So one way we could describe this is a positive feedback cycle is a shift in the environment that leads to another kind of shift that kind of comes and feeds back and creates more of the same shift in the same direction, or it accelerates the same change that we originally see. So it's kind of like a snowball effect. Like the snowball starts to roll, then it gets bigger, then it gets even bigger, now it's even heavier and bigger, now it's bigger, now it's bigger. So that would be an example of a positive feedback effect. And we can see this with changing albedo on the climate. So, or on the Earth's surface, which then impacts climate. So today the Earth is warming, and as it does that, it causes more ice to melt. When there's less ice, the Earth is less reflective. It lowers the albedo and allows it to absorb more energy from the sun. So that extra energy then warms up the Earth even more, which then melts even more ice, which makes the Earth even less reflective, lowers the albedo even more, which then heats up the Earth even more, which then melts even more ice, and we get caught in a cycle where the ice starts melting more and more and more rapidly. So that would be an example of a positive feedback effect. And we know we've lost lots of ice and glacial cover over the past century, and particularly over the last decade or so when the speed has accelerated. I was going to try to show you this little YouTube video here showing the Arctic sea ice, so up near the North Pole. This is the sea ice back in the late 80s when I was born. I was born actually in the early 80s. And you can see the ice cover changes a little bit from summer to winter. It always melts out some in the summer, but you can see how it's changing throughout the 90s. And then through the 2000s. And then you can see it's getting quite a bit smaller in the last 10 years. the ice is just really not sticking around. Even if it forms, it's not lasting for very many years. So there's a significant reduction in the sea ice, which is impacting, oh, we don't want to do that, the albedo of the planet. Oh, I'm sharing my screen again. Can I do that? Okay. Let me just make sure I'm sharing the right screen for you guys. Okay. Actually, that is the end of the video. So we'll stop there. Sorry about that. And then we'll come back and talk about greenhouse gases.